All right, folks, let's get this party started. Welcome to the end of the first part of the course. It's the end of the fifth week. We are going to finish covering the final chapter. We're covering chapter 6, and then we are going to take an exam on Tuesday. So I sent out the information on the exam on Tuesday, and if you have any questions about it, I'd be happy to address them. So do you have any questions about the exam? Yeah. No cheat sheet. No. Yeah, chapters 1 through 4 and 6. Remember, my lectures are the source of information you should be focusing on. Other questions about anything? Why is the sky blue? I can't address that question. Well, not just in case. Like, ideally, there will not be a need for a curve because everybody will get A's and B's, and that's it. But if that doesn't happen, then of course, yeah.
Will there be questions like there were some questions that I didn't see were addressed in the slides that were?
Yeah, anything I did in the homework is fair game too. Yeah. But remember, the homework is the basis for the true/false, and then the practice problems are the basis for everything else. So, yeah.
If you want to say a little bit more of like what you have on like the study guide itself, could you like refer to the book? Are those guys similar to? They have like practice problems?
I would not look at any other practice problems besides the ones that I presented, because you can potentially get confused by them, because some of them are meant to kind of take it a step further and challenge your ability to kind of understand the model, and I don't think that it's appropriate at this level to do that. So that's why I don't ask. People ask people to just not even look at those problems. Other questions? All right, folks. I expect you guys to work really hard. I've been expecting that of you from day one. So ideally, you have been working very hard this entire time, and this weekend is just about reviewing what you already know, besides what I'm going to cover today, which is, its own thing, and you will need time to think about it. But beyond that, like, it's all about just kind of like, going through the things you already know this weekend, not learning everything this weekend, because if you don't know enough, and I'm not talking to everybody in the room, by the way, I'm talking to everybody in the class, so people at home are listening to me. If you haven't been keeping up with this stuff, and you wait till the last moment, it is a recipe for the disaster. I have said that since day one, and I will continue to say it, because it is the nature of this course and how you do well in this course, for you to always be A, plugged into the course, and B, working on getting the information down that I'm covering. And if you're not doing that, I wish you luck. I hope all that cocaine you're going to use on Thursday night is going to pay off. Don't use cocaine; it's illegal and it's bad for you. But really, you're gonna have to pull a bit of a miracle at the last moment if that's what your approach has been. And I hope it works out for you. That's all I'm going to say. I hope it works out for you. Just remember, to the rest of you though that are working, regardless of how much you know the information and how well you can do the problems, it is timed as well. So there is that extra element to it. So yeah, you can sit and think through things and take however long to figure them out normally, but that's not a normal situation. There is a time frame that is the amount of time you will have to figure this stuff out. So that means that you need to be kind of fast on it as well. So it's not about casually knowing how to do these things. It's about knowing how to do them. So make sure you do know how to do them well. And you come in and you sit down, you see the problems, and you just start doing, got that one. Yeah, got this. All right, there's that. All right, done. A. That's what I want to see. I want to see it from all of you. And that's it. So I wish you the best of luck, and I hope it works out. I'm going to go through the final part of Chapter 6 today, and then it'll be in your hands. All right, so we're dealing with Chapter 6. Again, it's dealing with issues of uncertainty, where in reality, that's basically all we're ever dealing with. There's so much going on, you can never be quite sure about what's actually going to happen. You may not even be sure about how you feel about things. That may change depending on the situation. So we need ways of kind of incorporating that aspect of reality into the models in order for them to be a little bit more powerful in their predictive power. Ultimately, again, this is a social science because of that part of it, because you just cannot account for all the uncertainty. There's no way to really say things will turn out this way in the economy. Things will turn out this way in this market. This is how this price will change, over the course of the next 3 months. There's just no way to know. We didn't know Donald Trump was going to be elected. We didn't know that Britain was going to vote to exit a trade union that benefits them and all of Europe. Like, we didn't know these things would happen that makes sense to not happen. And so, again, there's a lot of uncertainty in life. We need to be able to incorporate that. The chapter introduces us to some of the concepts that underlie the approach to that incorporation, but obviously in practice, that approach is a little bit more complicated. You need to go a little bit further in your understanding of probability and multivariable calculus to really get to the level that you need to get to really truly know how these things work in practice. How they're working at central banks, how they're working at hedge funds, financial institutions, financial intermediaries, where all these things come into play every single day. They're always trying to figure out how to best predict the path of prices over time, and so this is a foundational course for you. And I hope that you do choose to build on that foundation in the future. But again, what we teach in this class is just meant to start you off in your understanding. But at the very least, if you don't go further, it provides you some intuition about the tools and the approach and maybe even the outcomes of the market that we can predict. All right, so we were looking at choice under uncertainty via the von Neumann-Morgenstern utility function, which we'll talk about again today. And continue on and sort of highlight the nature of incorporating attitudes towards risk into our models of choice. So that's what this first part's about. And then we can bring some of the insights and characteristics of the model as they are presented in the earlier part into the practical application of pricing insurance. So that's just sort of one way that we'll kind of make the connection between the abstract and the practical here. All right, so we started. So I'll just go back a couple of slides and kind of start up again your understanding of the von Neumann-Morgenstern expected utility model. So the formal economic theory of choice between uncertain alternatives was advanced by John von Neumann, a distinguished mathematician at the Institute for Advanced Study, and Oscar Morgenstern, a Princeton economist. The central premise is that people choose the option with the highest expected utility. They choose the option that's going to give them the highest expected outcome in terms of their overall satisfaction. We did some expected value calculations last time on 3 different gambles that you might face. And they had increasing riskiness. And even though the outcomes were better for the riskier options in terms of expected value, the average outcome that could occur, it was clear that you felt worse about the outcomes, given that you were not willing to take on some of the more risky gambles. And so that's really what we're talking about here. We're talking about expected utility. How do you expect to feel as a result of this gamble that you're taking on versus what you expect to happen within the gamble? And that needs to be incorporated into analysis. Expected utility is the expected utility of a gamble over all possible outcomes. So we talked about that fair coin being tossed, heads yielding $100, tails yielding 50 cents. If a consumer had a starting wealth of $1,000 and accepted gamble 1, the outcome would yield, of course, a total wealth of $1,100. So the consumer's utility would be their utility as a function of their net wealth after the gamble. So it's their utility would be how they feel about their wealth after the gamble. If let's say you lost, then your wealth would be 1,000 minus 50 cents, which is $999.50. So how you would feel about that is represented by the utility of that amount of wealth. Generally, if a consumer has an initial level of wealth, which in the example was $1,000, but in general is just M naught, then the expected utility of accepting gamble 1 would be equal to the weighted average of all possible utility outcomes weighted by their respective probabilities of occurring. So we've got 1 out of 2 chances of getting heads, so that's the probability of getting heads, one half, and the outcome would yield $1,100. And so how the feelings about that outcome is, of course, the utility of that initial wealth plus $100 in general terms, plus 1/2 the probability of losing, which means you get tails. It's 1 out of 2 options in this case. That represents the probability of getting tails, and so that is the weight, meaning the coefficient on the outcome, which is going to be measured in how you feel in utils. So utility of that initial amount of wealth minus the 50 cents. If she rejects the gamble, she would get the utility from the initial wealth. So if she says, no, I don't even want to deal with this, given what my expected utility is, then she's going to have some utility, some feelings about just the overall wealth that she already has, independent of the gamble, which is, in the example, $1,000, but in general, M naught. Faced with the choice, the von Neumann-Morgenstern expected utility criterion tells you to accept the gamble if and only if the expected utility of the gamble is greater than the utility of your initial wealth. So we went through an example. We said this is the utility function. It takes this functional form. It's a square root of the wealth. If Smith has an initial wealth of $10,000, which of the 3 gambles has the highest expected utility? We went through all 3 examples. So the first one had an expected utility of 1/2 times the utility of, again, getting that 10,100 plus 1/2 utility of losing 50, leaving the consumer with 10,000 minus 50 cents, which is $9,999.50. The square root of that tells us how this consumer feels about that amount of wealth. And so plugging all this stuff into the calculator, we figured out that has an expected utility of 100.248 utils. And then we did the same thing for the second option, and we did the same thing for the third option. We did this last time, by the way. That's why I'm going quickly. So gamble 1 is the most attractive because, again, it has the highest number of utils. The expected utility is the highest. Yeah, it's only 1,000th higher, but with utility, it's ordinal. It just depends on the numbers relative to each other. They have actual no meaning on their own. So just the fact that this one's greater than this one means that this option is preferred to this option. Did you have a question?
We did the square root because Smith's utility function is given. And then we were going to
Well, the previous example is just generally, so we didn't specify utility function. Yeah. So here it was specified. So yeah, you would be given a utility function. So the question is, should Smith accept the gamble? Well, we need to look at the von Neumann-Morgenstern expected utility criterion. Does the expected utility outweigh the utility of the existing wealth? We know that existing wealth is 10,000. Square root of 10,000 is 100. And so, yes, the expected utility of this gamble is greater than the utility of the existing wealth, and therefore, based on the criterion, the consumer should take the gamble. All right, so the key inside the theory is that the expected values of outcomes of a set of alternatives indexed by I need not have the same ranking as the expected utilities of the alternatives. So basically, again, like we looked at the expected values of the outcomes last time of those 3 gambles, which was just the weighted average of all possible outcomes weighted by their respective probabilities of occurring. So basically what we just did, but we didn't put the numbers into the utility function to add that extra layer of like subjectiveness to the outcome. We just left it as a number, and we weighted them by their respective probabilities. That's how we got the expected values. And we saw that they were ranked differently, but those magnitudes just told us something about the expectation of what could happen as far as the value of the outcome, the payoff, versus how a person feels about it. And that's where expected utility comes from. So in the empirically most common case, Utility is assumed to be a concave function of total wealth. We talked about utility in general. For most things being concave, meaning that they exhibit diminishing marginal utility. Each additional unit gives the person, consumer, positive amounts of utility, but less than the prior unit. So each additional unit has diminishing marginal utility, which is the slope of our utility function at any given point. So it's a derivative of the utility function at any given point, which tells us the marginal utility. And we see that it is getting flatter and flatter and flatter, which means that it is decreasing. So therefore, this amount of wealth has a much higher amount of marginal utility than this amount of wealth, meaning that as people have more money, they tend to enjoy money less. So more formally, a function, um, is said to be concave if for any pair of values m1 and m2, the function lies above the chord joining the points. So here's m1, here's m2, there's m1 and u of m2. So basically the combination of the wealth and the respective utility of that wealth. Again, here's another combination of the two. Joining the two together, you have this line, and if this line is below the utility function, then it's going to be concave, which again, it means that it's exhibiting diminishing marginal utility. And we need to define this in this way because you don't always, like we know, utility is a function of more than just one good in reality. It's a function of more of too many goods, really. And therefore, you're going to have a multidimensional relationship, which can't be represented graphically. And so we have to depend on definitions like this to maintain the characteristics that we need for it to be concave, even when we can't see it being concave. All right, so the utility function that we looked at a second ago, the square root of m, is a concave function of m. So that's one way we can represent your standard utility function. It exhibits diminishing marginal utility of wealth. Persons whose utility functions are concave in total wealth are said to be risk averse. So when we specify utility function that is concave, we are specifying that the agents, those making decisions to consume in our model, are risk averse. They are not willing to take on any kind of risk. They are cautious when it comes to taking on risk. So risk averse means a person has this characteristic if they would always refuse a gamble whose expected value is 0. Which means that they would always refuse what's called a fair gamble. A fair gamble is one whose expected value is 0. I'll talk more about what all this means in a second. So consider, for example, a gamble, G, in which you could win $30 if the coin comes up heads, but you lose $30 if the coin comes up tails. So here is the expected value of that gamble. 1/2 the probability of getting heads, winning 30, plus 1/2 the probability of getting heads and losing 30. The expected value of that is 0. So again, that's expected value versus expected utility, which would put these numbers within the utility function, and they would be weighted by their respective probabilities of occurring. In this case, because the expected value is 0, we have a fair gamble. For a person with an initial wealth level of, let's say, $40 and a utility function given by U of M, the expected utility of this gamble would be equal to 1/2 the utility of their initial wealth, 40, plus the $30 from winning, plus 1/2 the probability of losing, times the utility they get from their net wealth, which is their initial $40 minus the $30 they gain. So in that situation, we would have this expression here. We haven't specified the utility function yet. So for any fair gamble, the expected value of your wealth, if you accept the gamble, is the same as the certain value of your wealth if you refuse the gamble. So that's the nature of a fair gamble. So the expected value of wealth when you take the gamble is equal to 40, as we established there. It's here because, again, the expected value, you're going to get 0 from the outcome, and you're going to wind up with your 40 that you had. So that's the expected value of your of the gamble because it's a fair gamble. So the expected value is equal to, I forgot, I did the calculation for you. So 1/2 times 30 plus 40 plus 1/2 times negative 30 plus 40. So the expected value of your wealth is equal to $40 for this fair gamble. If you refuse a gamble, you will have a certain wealth level of 40, which yields utility equal to U of 40. The expected utility theory says that if the expected utility of the gamble is greater than the utility of your initial wealth, you should accept the gamble. Otherwise, you should refuse it. A risk-averse person would always refuse a fair gamble because the expected utility of the gamble would equal the utility of the initial wealth. In this case, your expected utility would equal the utility of your initial wealth because the expected value of the gamble is $40, which is the amount of your wealth, and therefore you feel the same about the expected value as you feel about your initial wealth, violating the criterion, which means that you, as a risk-averse person, would not take the fair gamble. So any gamble that has an expected value of 0, a risk-averse person will not take that. The expected utility of a gamble has a straightforward geometric interpretation. So here we've got, again, our utility function. So the expected utility of the gamble. So again, we're dealing with a situation where you have a $40 starting wealth. If you lose 30. If you win, you gain 30. So this is the losing outcome here. This is the winning outcome here. And there's our initial wealth level, 40. Initial wealth level 40 has a utility value of 32. If you win, you gain $30, so you have $70. So you'll feel 38 utils worth of happiness as a result of winning. And if you lose that $30, you'll have only $10 left, so you'll feel 18 units worth of happiness utility as a result of losing. So again, the expected utility is 1/2 the utility of the loss, which in this case will yield 18 utils, plus 1/2 the utility of the win, which is 38 utils. And so if you plug this stuff into your calculator, you wind up with an expected utility of 28 units. So we see that the expected utility of the gamble is actually, in this case, 28 utils, which is less than the utility of your initial wealth level. And that's due to the fact that we specified the utility function to be concave, representing the fact that and capturing the characteristic of a person who is risk averse, who is not easily willing to take on risk. So this value corresponds to the point of the chord between A and C that lies directly above the expected value of wealth under the gamble 40. So again, 28 corresponds to this point here that again lies above 40 along this chord that connects our winning and losing outcomes. And essentially what this is a line that represents all the possible averages that you can have of these two values, with the middle one being the one that has each outcome weighted by an equal probability, versus, let's say, one where you had outcomes like the outcome of winning to have a higher probability, so you'd probably wind up here somewhere, or if you had a lower probability, you'd probably wind up down here somewhere. But essentially what this is telling us is that the $40 wealth gives us a utility of 32, which is greater than the expected utility, the average of these two, which is 28. So the expected value of the gamble we know is 40. The utility of refusing the gamble, U of 40, is 32, which is larger than the expected utility of the gamble itself. And therefore, because the expected utility is less than the utility of the initial wealth, that implies that you should refuse the gamble. And again, it is all captured within the fact that we specified a concave utility function in order to include that attitude towards risk into the model. So the figure reveals that a risk-averse person will refuse gambles with positive expected values as well. So in this case, in general, a risk-averse person will refuse a fair gamble because it has an expected value of 0. But given the utility function we specified, they will actually refuse gambles that have a positive expected value as well. So for the particular utility function shown, all gambles that result in an expected wealth of final value less than 52 yield a lower expected utility than that of remaining with the initial wealth of 40. So if you were to change like the probabilities or even the payoffs a bit, and let's say the expected value of the gamble was somewhere between 40 and 52, then even those gambles would wind up with utilities, the expected utilities that would be less than the utility of the initial wealth, which is 32. So again, $40 gives this consumer 32 units of utility. The expected gamble as it stood had an expected utility of 28, which is below that. But then there's all these other values here between 40 and 52 that will also have expected utilities between 32 and 28, where the expected utility will be less than the utility of the initial wealth. And therefore, this risk-averse person would also refuse certain gambles that have an expected value less than 52. So that's just another thing to come to understand about like the nature of this consumer that we're modeling via a concave utility function. They wouldn't just refuse the fair gamble; they would actually refuse gambles that have positive outcomes as well. So they're very sensitive to risk is what I'm trying to drive home. You should understand the mechanics of it, of course. But again, this is like a very powerful approach because if you can account for the risky the attitude towards risk of the participants of the market that you're thinking about, then that can give you a little bit more certainty about your predictive power of your model, right? Like you might be looking at like prices of equities versus prices of bonds. People that deal in bond markets tend to be more risk averse than people that deal in equity markets. There's a bigger differential between the expected outcome of like a bond price versus the expected outcome of like an equity or stock price. So if you're trying to sort of track how prices are going to change, like attitude towards risk is pivotal. Is a pivotal component that needs to be included in the model. So this is how we go about doing it, and these are the characteristics of why it works. All right, so let's look at this example. Expected value of wealth. Your utility function is once again square root of m, and your initial wealth, let's say, is $36. The question is, will you accept a gamble in which you win $13 with probability 2/3 and lose 11 with probability 1/3? So now we got to figure out the expected utility. Excuse me. So the expected utility, of course, is going to equal, so if we're looking at the loss, what's going to be the weight on that? Like the coefficient on that term for loss? 1/3, and then what's going to be the utility? Not the actual number, but like how's it going to look in the equation? So I'm looking at the loss. So we're looking at the wealth, right? Wealth level minus 11, which is 25. And so it's going to be the square root of 25, right? Because we're looking at expected utility. Did you guys say that? Okay. I know a lot of you know what I'm talking about all the time, and I appreciate that. All right, so wealth level 36. Added bonus. Oh, this is from, I'm sorry, we're looking at I thought I had the losing term first, but I actually had the winning term first. So yeah, so 2/3 probability that they would win and get 13, right? So 2/3 times how you feel about your net wealth, which is $36 your initial wealth, plus the $13 you win. So this tells us how you feel about it. Your utility function is a square root function, so we know that you are risk averse, plus 1/3 times the square root of what? 36 minus 11, which is 25, as you guys had said. So just plugging stuff into the calculator gets us to, in this case, 19/3. If you refuse the gamble, though, what's your utility going to be a function of? Of what amount? 36, right? The utility of your existing wealth. So that's going to be the square root of 36, which is equal to 6. So your existing wealth gives you 6 units of util versus the gamble, which gives us an expected utility of 19/3, which is just slightly over 6, right? And so what's going to happen as far as the gamble goes? You accept it, right? The expected utility is greater than the existing wealth. So should you accept the gamble? Yes. So one intuitive rationale for the assumption that most people are risk averse. So we assume that most people are risk averse in general. So that's generally how we would specify the attitude towards risk for just like the benchmark most common case. So one intuitive rationale for the assumption that most people are risk averse is that increments of total wealth yield diminishing marginal utility in general. This has been proven empirically, like there have been studies, asking people how they feel about this level of wealth versus that level of wealth, ranking type, using ranking systems to generate the data. And that's the result we got. So an extra $100 means more to a person if his total wealth is $4,000 than it would if his total wealth is $1 million. The intuition is equivalent to saying that the utility function is concave in total wealth, which in turn implies that a given gain in wealth produces a smaller gain in utility than the loss that would be caused by a comparable loss in wealth. Meaning that if you go backwards along the utility function, loss hurts more than gain. So that's why people are generally considered risk averse. That's a pretty standard trait. Of course, not all people are risk averse. Some people are risk takers, as you can see by the empty seats in the class. Risk-seeking preferences described by a utility function with increasing marginal utility of wealth. So instead of having the what we call in calculus a concave down function, or also just concave, where you have that diminishing marginal utility, you actually have increasing marginal utility for a risk-seeking individual. So this would be the kind of utility function you would specify for, let's say, if you were looking at like hedge fund managers that are that are speculating on certain assets, and you were trying to figure out like how their behaviors would affect like the price of an asset over time or whatever. So consider a person with an initial wealth of M naught who's confronted with a gamble that has a half probability of either winning or losing some amount B. If this person is a risk seeker, her utility function will look like the one pictured here. So there you've got that initial wealth. There you've got the amount of loss. There you've got the amount of gain. That's the utility. That's how they feel about their win and their loss. The average of how they feel about it is their expected utility, which is going to be this amount, which is greater than the utility of their initial wealth. So for a person that is a risk seeker that has a utility function with increasing marginal utility, then they will accept a fair gamble. So it's convex in total wealth, which implies that the expected utility of accepting the fair gamble will be larger than the utility of refusing it. So therefore, they would take a fair gamble. So geometrically, a convex utility function is one whose slope increases with total wealth. And then, of course, you could have the in-between case, a person who is risk neutral. Preferences described for a risk-neutral person, their preferences are described by a utility function with constant marginal utility of wealth, which means that they just have like linear utility function. A person is said to be risk-neutral if he is generally indifferent between accepting or refusing a fair gamble. The utility function of a risk-neutral person will be linear, and the expected utility of a fair gamble will equal the utility of their initial wealth. So they'll be like right there where just they don't know what to do. They probably just would take it. So a risk-neutral person will take a gamble as long as it has a positive expected value. So if it's just slightly above 0, then then a risk-neutral person will take a gamble. Versus one who again is risk averse, and they would not take a a gamble that even has a positive outcome like we saw with the example we looked at. All right, quick example, quick practice problem. You have a total wealth of $10,000. You're asked to invest $2,000 in your roommate's startup. You reckon there's a 90% chance that the company will go bankrupt and you'll lose your entire investment, and a 10% chance that your stake will be worth $30,000. What is the expected value of the investment? So let's set that up first. So in this case, what is going to be the probability of winning here? 10% chance, right? And what is going to be the outcome to that? What's the payoff of that? 30,000 is what you would get, but there's something else you're not incorporating. We're looking at expected value of the outcome, right? Of the investment. So there's some money being invested here, right? Which no, 10,000 is your wealth. $2,000, yeah. Read the problem carefully. It's another challenge that most people seem to not conquer sometimes. All right, so anyway, yes. So the expected value, there's a 0.9 probability of losing, which means you just lose that $2,000, plus a 0.1 probability that you will win, and your stake will be worth 30,000 minus, of course, the 2,000 you initially invested. I think. Well, I asked you something weird earlier. I'm sorry. I got things mixed up. Anyway, this is how you figure out the expected value of this problem. Yeah.
Are you always gonna like do it that way, or is it ever gonna be like you invested and then your return is combined with 30 stuff? You know what I mean?
Well, we're looking at the expected value of the investment. If we looked at what's the expected value of your overall wealth, then you would include for the expected value. But the expected utility is dependent on your overall wealth. All right, so expected value in this case is $1,000. If you are risk neutral.
So when you say investment, you mean like how much you gain
from the overall investment opportunity that you engaged in.
So you wouldn't include your startup. You would just say how much money you made.
You would not include your are you talking about your wealth?
I'm talking about you wouldn't. It would be 28,000 is your investment. Is the yield of your investment rather than 30,000.
Exactly, because you have to take into account the cost of engaging in the investment, right? Yeah, whatever your upfront costs were, whatever you use from your wealth to engage in the investment. All right, so if you are risk neutral, should you invest? Well, we have to see, right? We have to see if we know that it has a positive expected value, right? So that tells us something, given what we know about risk neutral people. Risk neutral people will take outcomes that have positive expected values. So the expected value is greater than 0. And so yes, because of that. Now assume that your utility function is m raised to the 1/3 power, which is going to be concave, right? So therefore now we are saying that the consumer is what? Risk averse, right? So M is again your wealth. The question is, should you invest? So what do we have to compare here? Of what? All right. But you have to include wealth in there as well. So the expected utility of your wealth after the investment as compared to what? Right, but what about that? The utility of your initial wealth. The utility of it. But I know you knew what you're talking about. But we have to be very specific here, right? All right, so the utility from no investment, of course, is just the utility of $10,000. So 10,000 raised to 1/3 power, which is 21.54 utils. The expected utility of the investment, again, you're going to have that 0.9 probability of going bankrupt, which means that you're going to lose $2,000 from your $10,000 in wealth. So you have a utility of $8,000 there, plus a 0.1 probability of actually having a successful investment. and therefore you having your $10,000 in initial wealth plus the $28,000 net of your investment that you walk away with. So adding those together will get you some level of satisfaction, some utils. So plugging in 8,000 raised to the 1/3 and 38,000 raised to the 1/3, and then weighting those by the respective probabilities of occurring, and plugging everything into your calculator properly, acknowledging the order of operations, will get us to 21.36 utils of the investment. So should you invest? No, right? The utility from not investing is greater than the expected utility of the investment. Do not invest. Yeah.
But even though it, let's say, was 21.64, you still would not invest, correct?
If what was 21.64?
Like the expected utility investment.
If it was 21.55, you should invest. Because remember, it's ordinal. So it just matters like how big it is relative to the other number. So it's just a ranking system. So therefore, if it's even just up by just a hundredth of a point, it makes sense to do it based on the criterion that we're following. What is the minimum probability of getting the 30,000 for you to do the investment? All right, so for you to do the investment, you would need the expected utility to be higher than the utility of your initial wealth, right? So basically what you need to do is you need to set up that expression, and P is going to be the variable in this case. You need to solve for the probabilities. So the minimum probability of getting the 30,000, so that's the probability of you doing well, and therefore we're solving for this probability. So we're not saying it's 10%. We're saying what is the minimum probability that would get you to do the investment. So if we let P equal the probability of the investment working out, we know the utility of no investment is equal to 21.54. So if we set that equal to 1 minus P, and then we have 8,000 raised to the 1/3, which is what you would get if things did not work out. So 1 minus P is the probability of it not working out, plus P times the outcome if it did work out and how you feel about it. So here you need to distribute this out. Well, first you solve for these numbers, and then you distribute them out. And what we wind up with is 20 minus 20p equals 21.54. Plus 33.6p is this term here. And I subtracted 20 from both sides there. I combined these terms there, and I divided both sides. So that's 11.3%. So if it's just like 1 percentage point above that, then the expected utility would be greater than the utility of your initial wealth, and therefore you would accept the gamble. Just a little bit of math trickiness there, but not too tricky because I'm showing you how to do it. Yeah. It would be above it because the percentage would be above it, right? So the percentage of the good outcome is higher than here, where that 11.3, which equates these two, and therefore it would wind up giving the consumer a higher level of utility.
So 11.3%, you would be indifferent to doing the investment or not.
Exactly.
And then you just bump it up very marginally, and then you would live with it.
Right. All right. So exposure to risk is an undesirable thing for risk-averse consumers, as we know, enough so that they're often willing to sacrifice substantial resources in order to reduce it. Insurance. So in order to price insurance, we have to use what's called the certainty equivalent. The certainty equivalent value of a gamble is the sum of money for which an individual would be indifferent between receiving that sum and taking the gamble. The certainty equivalent value of a gamble is less than the expected value of a gamble for risk-averse consumers. I'm going to show you what that is right now via a practice problem. So let's say your current wealth is equal to $108 and your utility is m raised to the power of 0.5. John Smith offers you an investment opportunity. There's a 57% chance that you'll make $25 and a 43% chance that you'll lose $5. What is your expected wealth if you accept the offer? So now we're looking at expected wealth, right? So now we're going to do an expected value with the wealth. So we got 0.57% chance that you'll get $25 added to your $108 plus a 0.43% chance of losing $5. So subtracting that from your $108. So that's your the expected value of the expected wealth of net of the gamble. What is your expected utility if you don't accept the opportunity? So if you don't accept the opportunity, obviously your expected utility is your utility of your wealth. So just plugging in your wealth into your utility function gets you to, in this case, 10.39 utils. So that's your initial wealth level, and that's how you feel about it, 10.39 utils. What is your expected utility if you do if you do accept the opportunity? So now we got to set up our expected utility expression and figure out what that is. So again, basically similar to what we did in the first problem, but we're going to plug each of our net wealth values into our utility function. So we've got 0.57% chance of winning, and so that's going to weight the outcome. So utility of 108 plus 14 plus the 0.43 chance of losing, which is going to weight the utility of your outcome, which is 108 minus 5, which is 103. Plugging our utility function into that to get how we feel about each of the outcomes, multiplying them by their respective weights, gets us to the expected utility of 10.93. So 10.93 greater than 10.39, so the gamble will be taken, of course. So that's one possible outcome. You get $122. That carries a utility value of 11.05. You could lose and carry a utility value of 10.15. And so the expected utility is the average of these two, which winds up being, in this case, 10.93, which is greater than 10.39. How much wealth do you need for sure to get the same level of expected utility as in the previous part? So how much wealth would you need to be as happy as you are with the gamble? So basically, we figured out our expected utility, and now we need to figure out what is the amount of wealth, M, that would give you that amount of utility, independent of the gamble. So we plug in 10.93 into our utility function. That's our utils. And we're trying to figure out what is this level of income, wealth, overall wealth, that would make us that happy. So we need to solve for this. How do we solve for this? Right. What kind of math approach should we take here? We need to square both sides, right? So this is being raised to the power of 0.5, so we need to raise both sides to the power of 1 over 0.5, right? That would cancel out to 1, and 1 over 0.5 is equal to 2, so we're essentially squaring both sides. Squaring both sides will get us to 119.46. So $119.46 would make this person as happy as the gamble is expected to make them. This is what's called the certainty equivalent value. It's the sum of money for which an individual would be indifferent between receiving the sum and taking the gamble. If they had that money, then the expected utility would be equal to the utility of their wealth, and so they would be indifferent between taking the gamble or not. That is the certainty equivalent, and it is something that is used to price insurance, and we'll see how right now. So again, what we figured out here, remember we figured out what the expected utility was, which is the average of these utility values, which is 10.93. Now we're trying to figure out, now we figured out that the amount of wealth that makes a person that happy is equal to 119, whatever it was, and that is the certainty equivalent value. All right, now let's talk about insuring against bad outcomes. So when the risks that different consumers confront are independent of one another, That is when the likelihood of a bad outcome happening to one consumer is independent of the likelihood of one happening to another consumer. It's often possible for consumers to act collectively to achieve a result that they all prefer. Risk pooling is what we call it. So recall gamble 3, a fair coin toss. Heads gets you $20,000, tails loses you $10,000. Suppose you could join 9,999 other people in an agreement under which you accept the gamble, then pool the resulting gains and losses and share them equally. The only way you could lose money under that agreement would be if 10,000 flips of a fair coin came up tails more than 2/3 of the time, which is highly unlikely. So risk sharing or risk pooling works because of the statistical property we call the law of large numbers. The law of large numbers is a statistical law that says if an event happens independently with probability p in each of n instances, so n different times, the proportion of cases in which the event occurs approaches p as n grows larger and larger. So if we're talking about getting heads or getting tails, we know that 1 out of 2 times you'll get heads and 1 out of 2 times you'll get tails. Based on what we know about our options. If you repeat the coin toss an infinite number of times, and the law of large numbers says that half the time you will get heads and half the time you will get tails. So the amount of times you actually get an outcome will approach the probability of that outcome as you increase the amount of trials. That's what the law of large numbers says. For individuals or even small groups of individuals, accidental losses pose a problem of inherent uncertainty. But for large groups of individuals, the proportion of people who will have accidents is extremely stable and predictable. The law of large numbers makes it possible for people to reduce their risk exposure through pooling arrangements. Partnerships, joint stock companies, and a host of other similar institutional arrangements enable people to translate unacceptably large risks into much more palatable small ones. Consider the case of automobile liability insurance. Private insurance companies offer a means for consumers to share the risk of an accident that causes death or serious injury, resulting in a court judgment of several $1 million against the driver. Contributing an annual premium of $700 each, the policymakers create a pool of revenues that's large enough to settle the small handful of judgments awarded each year. Because of the law of large numbers, insurance companies can predict very accurately how much revenue they will need to cover their benefits claims. Each party accepts a sure small loss, which is the premiums that we pay, in return for a guarantee of not having to bear the much larger risk. So then the question is, how much are people willing to pay to be part of those pooling arrangements, which is insurance? So what's the most a consumer would pay for insurance against a loss? All right, so again, here's our utility function. Let's go through the story of what's happening on the graph. Suppose a risk-averse consumer with an initial wealth level of $700, so they're starting off with $700, and they have that utility function. If he faces a probability of a loss of $600 with probability 1/3, so you can think of it as like a person that owns a house, and let's say it's worth $700,000, and there's a 1/3 probability that there's going to be a hurricane and they're going to lose $600,000 worth of value in the home. Like, you can think of it that way. Then the expected utility of this person is, of course, going to equal 1/3 the utility that the loss actually occurs. So this is the amount of wealth that they have, 700. If they lose, they're going to wind up with only $100. They feel 18 utils worth of utility for that $100, plus 2/3 probability that nothing will happen and there's no hurricane and they keep their house and they're happy. So then they have a utility of 700 here, which is going to be equal to 36, and this one's equal to 18. So the expected utility is equal to 1/3 times 18 plus 2/3 times 36, which is equal to 30 here. So that's the expected utility of the gamble of having a home in like a hurricane-prone area, let's say. Prone meaning there's a third probability that during hurricane season, a hurricane will hit. So that's how they feel about it. Suppose the consumer could buy an insurance policy that completely covered the loss The question then becomes, what is the most that he would be willing to pay for such a policy? So the figure shows that if he paid $330, his utility would be, so he's got $700 there. If he were to pay $330, then the utility in this case would be 30, right? 700 minus 330 is utility of 370, which is equal to 30, whether or not a loss occurred. Since this is exactly the same as his expected utility, if he did not buy the policy, he would be indifferent between buying and not buying it. So his reservation price, what he'd be willing to pay for the policy, the most that he'd be willing to pay for it is thus going to be the $330. So remember, the 700 minus the 330 is equal to 370, and that is going to be the certainty equivalent of this gamble of living in this area. The expected utility of the gamble is equal to 30. If we look at the amount of wealth that gives the consumer that much utility, it's $370. So that's the certainty equivalent of living in this hurricane-prone area. All right. If I is the actual price for the insurance, and it's less than $330, and the consumer will buy the policy and get consumer surplus in the amount of 330 minus I. So this is how much wealth they do have, but they could wind up with only 100, but they're willing to pay 330 to avoid that possibility, and therefore, if they pay anything less than 330, they are going to have some consumer surplus. Their reservation price, the price they're willing to pay, is $330. That's the most they're willing to pay. But, based on the amount of people in the market buying the insurance, the price actually might wind up being less, and therefore they would have some consumer surplus. So let's do a problem where we can calculate the reservation price of insurance. So you have a utility function, m equals, u of m equals m raised to the 1/2 power, where your initial wealth is equal to 100. There's a 50% chance that you're going to lose 36 bucks. What is the most you'd be willing to pay to insure against the loss? So the first thing is you want to solve for the expected utility of the gamble, right? That's how you're going to figure out your certainty equivalent. So there's a half probability that you are going to be fine and not lose anything and just have your $100, plus half a probability that you're going to lose $36 and you feel this much about it. Plugging those numbers into your utility function, weighting them by the respective probabilities of occurring, gets us to an expected utility of 9. How are we going to solve for the certainty equivalent? What's the amount of money that's going to make a person as happy as the expected utility here? How do we solve for it? How do we set it up? 9, yeah. 9 equals m raised to the power of 0.5. Right? We're trying to figure out what is the amount of wealth that would make the person that happy as the gamble would, given the expectations. So solve for the certainty equivalent of this gamble. So you put 9 equal to the utility function in order to solve for that level of wealth. So raising both sides to the power of 1 over 0.5, so basically squaring both sides, gets us to the wealth of $81. So $81 is the certainty equivalent. So what is the most this person is willing to pay for insurance? 19 bucks, right? The difference between their initial wealth and their certainty equivalent. That's the reservation price for insurance. It's equal to 100 minus $81, which is 19 bucks. The reservation price of insurance is initial wealth minus the certainty equivalent. All right, just a couple of ancillary issues to discuss in relation to insurance. There's a couple of possible scenarios that could result and do affect the insurance industry. One is of adverse selection. So adverse selection refers to a situation where a selection process results in a pool of individuals with economically undesirable characteristics. So if you're a car insurer, well, obviously in California, everybody's expected to buy car insurance. But let's say that wasn't the case. Then insurance companies would likely attract people that are going to be most likely to drive dangerously, right? Like the pool of possible candidates are going to be people that are going to need insurance. People that take out loans are generally going to be people that need money, and so there's an adverse selection problem in lending because that is going to put the lenders in precarious positions if they attract people that need money and therefore are more likely to not pay back money. So there's an adverse selection problem there. So adverse selection is especially relevant to insurance markets where it often eliminates exchange possibilities that would be beneficial to both consumers and insurance companies. To remain in business, an insurance company must have revenues from premiums that cover the claims it pays out, plus its administrative expenses. Its premiums, therefore, must closely reflect the likelihood of claims being filed. Not all potential consumers are equally likely to file claims. In automobile collision insurance case, for example, some drivers are several times more likely to have accidents than others. If insurance companies could identify the most risky drivers, they could adjust their premiums accordingly. Without any broad category of policy, there will inevitably be wide variation in the riskiness of potential policyholders. The other problem that it needs to be considered is that of moral hazard. If you're protected in a situation, then you're more likely to take on a risk. So if you think about the 2008 financial crisis and the fact that the government stepped in and bailed out all the banks with the TARP program, which was $1 billion, that essentially created the notion that it's okay for banks to take on risky behavior because in the end, if it all hits the fan, they are going to have the government bail them out. So there's a moral hazard problem that was created as a result of that situation. So moral hazard incentives that lead are incentives that lead people to file fraudulent claims or to be negligent in their care of goods insured against theft or damage. Because the amount an insurance company charges in premiums must be sufficient to cover the amount it pays out in claims, fraudulent insurance claims cause premiums to be higher than they otherwise would be. Taking precautions is costly, and people who know their losses are fully covered by insurance are less likely to take them. And so because of that, they have to wind up engaging in the approach called statistical discrimination, which basically makes them kind of pool all kind of categories of people into one group versus another to kind of rein in the possibilities of sort of outliers. So automobile insurance companies often try to tailor their rates to the driving records of individual policyholders. In addition, most companies charge different rates to people with identical driving records if they happen to belong to groups with significantly different average risk. Male drivers under 25 are all charged higher rates since insurance companies cannot differentiate between those that are good drivers and those that drive like they're in the Fast and the Furious franchise. So just know what moral hazards, statistical discrimination, and adverse selection are. Just understand what those concepts are. All right, folks, beyond that, we are done with the first part of the course. Everybody hold on for a second.